Hello everyone, today we're going to continue our analysis on the reversible turbine that we talked about last time. This time we're going to focus on part B, which is the rate of entropy production within the turbine per kilogram of air flowing. And essentially that's asking us to solve for S dot generated over M dot. If we want to solve for that value, we need to know the entropy balance. And if you can't find that in your notes, it's probably somewhere in the textbook. And I already got that for you. It's actually, if you go to page 374, you'll find that equation. And it is, let me write down this equation. So it is Q dot over T. Let me rewrite this. It's Q dot over T plus M dot S in minus M dot S out plus S generated dot is equal to S dot CV. And below that equation, the textbook describes that when it is steady flow or it's steady state, this S dot CV is 0. So that makes our life easier. And our goal is to rearrange this equation so it is S dot generated over M dot. So let's do that. So if we divide all these terms by M, then we'll have Q dot over Tm dot plus S in minus S out plus S dot generated over M dot. That is equal to 0. And our goal is to find this value. So we can just move everything to the right except for this term. So it's just S dot generated over M dot is equal to, I'm going to flip the sign of this parentheses. So S out minus S in minus Q dot over T M dot. Okay, and this S out minus S in can be rewritten into CP natural log T out over T in minus R natural log P out over P in. And then minus this term, Q dot over T M dot. So this T here, let me highlight this T a little bit. So this T here is this surface temperature, 315, okay? Just so you don't mix that with the T out and T in. If you don't remember what T out, T in are, we can rewrite them here from the problem. So we know that T out, P out, so T out is 670 K, and P out is 100 kilopascal. And T in and P in, so T in is 970 K, and P in is 400 kilopascal. So our goal now is just plug and chug, but be extra careful with this R here. Okay, so we're not going to directly plug into this, plug in this RU into this equation because R is actually RU over the molecular weight here. Okay, so now let's do the math here. So I'm going to put everything back here. So CP, we know it's 1.1, and natural log T out over T in. that's 670 over 970. Minus, so it's RU over M, the squiggly M. Let me just rewrite this M a little bit so it's clear. Okay, so this R is 8.314 over 28.97. So that is going to, so times, so I'm going to write this, okay, let me try if I can do this natural log here. Natural log, yay, did it. What's P out? P out is 100 over 400. Okay, so this thing, and then minus, be extra careful here. This Q dot we mentioned in the previous video, this is heat loss. So it is going to be a negative value instead of just positive. So I'm going to use, so this Q dot over M dot here, it is negative 30. So let's put negative 30 over this T, which is 315. Okay? So if we work out the math, it's going to be 0.086 kilojoule per kg K. Okay? And since we have a little extra space here, we're also going to mention part C a little bit. So the last part asks, does an isentropic process serve as an ideal model for this turbine? Well, if it's isentropic, it has to be both adiabatic and also reversible. Alright, I hope this video helps you understand this problem better, and let me know if you have any questions. Thank you!